In the previous video, we talked about the digital I/O pins of the Atmega 328P, which is the microcontroller used in the Arduino, and that this circuit here is a simplified representation of the digital I/O pins. And I say simplified because the actual representation looks something more like this. And while this does look a little more daunting than the other circuit, it's really not functionally that different from what we see here in this schematic. We have our input side here, the output side here, and the major difference is that there is a optional pull-up resistor you can enable. The other differences are just more advanced control circuitry, and as well as some other circuitry in here to stabilize the signal. But for the sake of simplicity, I'm going to keep using this circuit, but I'm going to make it even more simple than this. That's because in this video, we'll be talking about the analog to digital converter. And if we take a look at the datasheet again, this is under alternate port functions. We can see here this is the input pin, and all of this right here is digital logic. What we have down here though, on this wire, which comes down in here and goes to here, is the analog I/O. So we can see that this wire coming down here completely bypasses everything else in the circuit. So we can basically ignore everything in the circuit. And this is what I meant when I said that the analog and digital pins really are not that different from each other, because each of the pins has this general arrangement of circuitry, but not every pin has the analog capability. And the pins with the analog capability, the only real difference is that there's an extra tap coming off that goes to a different subcircuit. So what I'm going to do is I'm going to take this circuit and remove everything and replace it all with just a piece of wire. And just imagine that piece of wire is this piece of wire right here, which is bypassing all of the digital circuitry. And that wire is attached to what's called the analog to digital converter, which I'm going to represent with this, along with this counter here so we can take a look at the value. Now the Atmega 328P only has a single 10-bit analog to digital converter, but that single ADC is shared among 7 pins. These 7 inputs go through a multiplexer, so only one of these pins is active at a time. This means when you call the analog read function, it's only ever able to read from a single port at a given time. If you want to read from 2 ports, it's going to have to do one after the other. So while logically it looks like this, where you have your 7 inputs and then it chooses between which input it's reading at any given time, we're not really going to worry too much about this. We're just going to stick to a single input because that's really all we need to worry about for right now. So the high-level overview of an analog to digital conversion is, firstly, the input pin has a signal going onto it. So imagine this is the input pin of the Atmega chip, which has a sine wave going into it. The first step is that it goes through a circuit called a sample and hold buffer, which is this circuit right in here. And what this does is if I press the switch here, you can see that it captures and locks onto the value of when I press that button. So if I hold it down, you can see it follows the output, but as soon as I let it go, it's going to maintain the last value seen from this switch. This is needed because the conversion process takes some time, and we need to make sure that the value it's trying to convert doesn't change suddenly during the conversion. Once the sample and hold buffer gets its value, it then puts it into the analog to digital converter. The ADC then takes that input voltage, compares it against an internal reference, and calculates a binary value representing that level of voltage. Now the Atmega chip uses what's called a successive approximation ADC, which means that it takes this value from the sample and hold buffer and divides it down repeatedly until it gets a closer and more accurate value. And it does this through multiple passes, which is why we need to have this value remain stable, which is why it's used from the sample and hold buffer. So, for example, in this graph, if we say that our sampled voltage is 11 volts, which is right here, what it's going to do is check first here and see which is greater or less than. Then it takes the path up here, does that same test again. Is it greater or less than? Goes down here, does it again and again and again until it eventually reaches the output value it needs. Once that conversion is finished, the ADC will report back to the MCU with a value that represents that voltage level. And keep in mind, this is just a very high-level overview of how the ADC process actually works. But for all intents and purposes, this is the flow that happens inside the chip when you call analog read. So far, we've talked about analog read, but we haven't said anything about analog write yet. And the reason for that is that there is no analog write, not really. Which I know sounds kind of weird because there is an analog write function. But that's a lie, because the Atmega chip does not have the ability to put out an analog signal. The only thing it's able to do is output digital signals. So when you see analog write, what they actually mean is pulse width modulation, or PWM. So counterintuitively, the analog write function is completely different from the analog read function. So I hope this video helped you understand a little bit better about how the ADC works in the Arduino, and I'll see you in the next one.